Hi, my name is Ben. I'm with Rigetti Computing. The title of my talk is probably way too long. It's just a list of things I will be discussing. But yeah, I'll be talking today about scaling up quantum processors with a chiplet-based architecture using intermodular tunable couplers and 3D integration. Just sort of a list of things that I'll discuss a little bit. I think this is more or less going to be a talk, but I'd like to make it a little more interactive than just a talk, in the sense that this is not just me showing the cool technology that we have and then showing a bunch of figures about how it works fairly well. I like to actually sort of go into the details of like what it's like to design with this, the things you need to keep in mind when you're designing with these things, sort of where these components can become a tool in your toolbox and how they can be a little bit challenging as well. I mean, feel free to ask questions as we go along. So Rigetti Computing is a full-stack quantum computing company. This means we do pretty well every piece of the quantum computing stack, from control systems down to, of course, the quantum processors themselves. We're based out of Berkeley, California, and we have our own fabrication facility in Fremont, California. It's very nice having our own fabrication facility. This means that, for one thing, we get a very repeatable process, which is kind of the dream as a designer. And it also means that we get fairly fast turnover, especially considering the complexity of our systems. So at Rigetti, our technology stack is quite focused on scaling. That includes things like vertical signaling, which is really important when you're going to large-scale systems, which I'll talk a little bit about later. I'm not really going to talk about sort of the whole stack that I've shown there, the package and whatnot. But the main idea is that all the signals are coming down almost entirely vertically from coaxial cables down to the actual QPU. We use a chiplet technology at Rigetti, which I think is quite unique. So this means instead of making everything on one monolithic silicon die, we break things up into silicon dies, silicon chiplets, and then we can connect them together. Of course, by far the hardest part about that is how do you do entanglement between chips, which we have been able to do, and so we'll talk about that a little bit later. Being able to do 2 Q gates across qubits that are not on the same silicon die. And so we'll talk lots about that. So for 3D signal delivery, this slide is sort of showing Rigetti's technology in 2017 versus 2024, but I think it's maybe more illustrative as a technology stack that people in academia might be more familiar with, which is the somewhat unique versus the somewhat unique stack that we have here. So when you're doing everything on a planar die, generically you're routing signals in from the perimeter. All of your elements are going to be on, of course, one silicon surface. This gets hard already when you're in the tens of qubits, and it's pretty well hopeless at 100 qubits. Every cable needs to be coming in from the edge. Of course, if you have sort of like 2.5 dimensional, then you can go quite a bit beyond this. But if you think about entirely planar, this really doesn't work well at a large scale. But when you have things in 3D, you can bring signals in vertically, and this really is sort of how things need to be done at a large scale. So the stack here, there's a PCB. Obviously, coaxial cables are coming onto the PCB. We then have a superconducting compliant interposer layer that allows us to get from the PCB onto our chips. And then our stack consists of 2 chips, a sort of a cap chip, which is also still silicon, and then the actual qubit chip, or we call it the QUIC, quantum integrated circuit. And there's through silicon vias through the cap chip that allow us to have like full 3D signaling to come through from PCB down to the qubits. This is a picture here of one of those vias. These are actual holes through the chip. And then everything else here is metallized. There's a sort of a few different layers there because, of course, it's a multi-layer process. And then this area here is actually etched away. So this is a pad where one of the compliant interposers touches down, and then from there the signal can route down through the via, and then ultimately that's going to be coming through into the qubit chip. And so this is really how things sort of need to be done at a large scale. And I'll talk a little bit about what it's like to be designing with these things. Okay, so actually I'd like to sort of say thank you to some of the people I've spoken with over the course of this workshop already. It was not immediately obvious to me what parts of designing with flip chip are interesting or complicated versus which parts are sort of immediately obvious. So this slide I prepared within the last 48 hours, just sort of like, okay, let's actually start off with like, what is flip chip? I guess that's not like a super obvious idea. So the basic idea with flip chip is sort of as the name implies, you have 2 different chips, you can pattern on both chips, and then you literally flip one on top of the other. And so you connect them using superconducting indium bumps. So indium is a superconducting metal. It's also a very soft metal, so it almost acts as a little bit of like a glue. And so by putting bumps down all over the chips, when you put one on top of the other and squash them, it actually creates a physically strong connection that is superconducting, and you can send signals through quite nicely. and then a sort of unique feature of Rigetti's technology is that we also etch a superconducting cavity into this chip. This is not a cavity in the sense of a resonator. It's a cavity in the sense that it kind of literally looks like a cave. We eat into the silicon that creates this sort of topology to it, or topography to it. And then the really nice thing about this is it means that the distance between the qubits and the cap is not exactly the same as the distance between the two chips. Right? For indium bump technology to work, you have to have a specific distance between the chips. It's quite short, but that's not necessarily the same distance that you'd like your cap layer to sit above the qubits. So it works really well to be able to do this. So this is not necessarily mandatory for flip chip, but it ends up being really, really helpful. You know, when you talk about designing with flip chip, one of the sort of challenging things about this is that your circuit now is not entirely lithographically defined, right? When I'm designing something for a planar circuit, I'm using lithography, which is very consistent, very repeatable. Even if you're doing UV lithography, it's like very small feature sizes. And that defines my entire circuit. So, you know, if I want a capacitor that's, you know, a 20 micron gap, like I'm getting 20 microns pretty well every time. When you have electrical components on two different chips, you know, that's not necessarily always a guarantee. And so, you know, sort of one of the questions I got earlier is like, how do you design for that if you have like, you know, several microns of variation? And the answer is you don't. You just really have to do really challenging fab, really challenging packaging to make sure that it's not several microns of variation. You know, and that means you both want to be really, really consistent in the standoff height, and then also really consistent in the lateral height. And so with just really good metrology, you know, markers, all these sorts of packaging technology, you can get to within just a few microns of error. But even then, you sort of notice that there's a bit of a systematic shift to it. And so when you really do all this, you know, sort of, you know, empirical corrections and all that, you can actually get down to sub-micron alignment. It's not easy, but it is doable. Mm-hmm. Oh yeah, for sure. So I mean, so it's one of the really important things is if you're like 3 microns away, then yeah, you're really sensitive to these things. So that's one of the other advantages to having this etched cavity, where like your actual effective distance is not, you know, 3 microns. It's now but 25 microns. So the, you know, you sort of do like Pythagorean theorem, right? They're like 25 microns plus or minus 1 is, you know, actually a distance is basically still just 25. Not the standoff height between the two chips, right? That's a few microns, about 3 microns. That, you know, then that's just like required by, you know, bump bonding technology. But then when you eat away the die in certain regions, you know, namely like the regions over top of, you know, certain electrical components, then the actual distance between, you know, the qubit and say the charge drive line, that is now you know, close to 30 microns. And so that gives you a little bit of insensitivity there. Another really cool trick is so the, you know, you might sort of think, okay, so I've got this, I've done this flip chip. How do I know that I've lined up, or how do I know how well I've done? Something really nifty is that the band gap of silicon is a little over 1 electron volt, which corresponds to a wavelength of 1100 nanometers. So that means that it absorbs all light in the optical spectrum, and this is why silicon dyes look opaque to us. But that means that you're transparent to almost the entire IR spectrum. And so what you can do here, so this is a picture of a chip I'll talk about later. So the black dots there are the vias. These larger kind of white dots are actually where you've etched the metal away on top of the die. You've done the same thing on the bottom die. You've got an alignment marker, you know, underneath this on the qubit chip. And if you look through with an infrared camera, you're actually just looking through basically glass, and you can see exactly how well you lined up. So this is kind of a nice little trick. You don't think of silicon as being transparent, but to any infrared camera it is. So this allows you to verify that you've gotten your submicron alignment, and you know that you're doing things well. The other nice thing about being able to vary the sort of effective standoff height seen by the qubits is that you can kind of now do a bit of like screening. You can make sure that you're like blocking things out and getting rid of crosstalk in that way. Yeah.
Design these for expanding on chiplets.
I will talk lots about how you sort of fit this into a chiplet architecture later. I'm not sure. Yeah, I will be covering quantum transactional memory in this. Yeah, so okay, so there was a really nice talk by Nicholas Zani from the Scholkopf group at the APS Summit this year. So they also have a similar technology they developed recently, and they were looking at like the optimal height of this micro machining that they do. And I think they found the optimal height is like 24 microns. And this is just accounting for various losses, right? Sometimes this is a more lossy surface. We also worry about crosstalk. So I think we've been doing this height since 2015, but I'm glad that it's now sort of open in the community. This is kind of the optimal height when you factor in things like loss and crosstalk. I have to imagine this is sort of a little bit dependent on what actual loss channels you have, but yeah. So I mean, it's just balancing a few different factors, right? If you go too far away, I mean, you do want there to be an interaction, right? 3 microns, that's way too close. You're going to be way too sensitive to just everything. But you don't want to be 100 microns away because ultimately you do want to be sending signals between these 2 different layers. So like there's sort of competing factors here, and it turns out this is just a nice sort of middle ground to land in. So another sort of set of questions I've gotten that I figure might be worth doing is just, okay, so I mean, let's say we're all sort of experts here in simulating and modeling superconducting chips, but of course we by and large do this in 2D. How does this look when you do it in 3D? And the answer is, for the most part, it's not all that different. So actually building the model, if you don't have an etch topology, it's super simple. Instead of having a GDS file for your qubit chip, you just have 2 GDS files. And then when you load them into your modeling software, it's really just one GDS file, another GDS file, give them their offset. It's pretty simple. Then extrude and get your bulk dielectrics. But it's really not that complicated. If you have an etch topology, this can be a little bit tricky. I can't really give a whole lot of advice because it's going to depend on like what simulation software you're doing. But there are techniques for doing this sort of like 3D modeling. Use sort of whatever Boolean operations are available in your software package, and it sort of works out. It's not necessarily easy, but it's also not particularly challenging. More annoying than anything else. If you have other 3D signaling, I mean, this is basically just a CAD problem, right? I mean, mechanical engineers do this all the time, figuring out how to draw 3D shapes and then loading them into modeling software. So, you can either use built-in tools or sort of draw them yourself. VIAs can sometimes have somewhat non-trivial shapes, so you may want to account for that. Yeah.
How do you model? I know, for example, with things like the reactive signal connection, you get this caliphate surface on the.
Yeah.
How do you model for that? So this can matter. I mean,
yeah.
Kind of a ideal, time wall, right? Change the RF property.
Yeah. So I mean.
Especially caliphate can be a place where filter gets concentrated.
Yeah. So to some extent, I mean, you want to understand your own process, know exactly what effects actually appear. If you're using this process and you have the scalloping. And then draw the 3D models accordingly. I mean, obviously, if there's some variability to your process, then you're probably not going to know that beforehand when you're doing simulations. But I mean, you do the best you can, right? But you do want to get a little bit creative, and actually like really try to capture your fab process as best as possible. So this is really where it helps to have a really close feedback loop between yourself and your fab team and really understand, okay, what do these vias actually look like? Where actually is the metal going? And like, let's get the best model we can. But it really ends up just being sort of case by case basis. For like tips and tricks on drawing these 3D shapes, I suggest you talk to like a mechanical engineer because they're kind of wizards with these kinds of things. But it's not like a tough physics problem. It's sort of just like, how do I draw some complex 3D geometry? It's a CAD problem, really. As for running the simulation, I think there were some comments yesterday about how in Idealist Palace and that sort of whole workflow using Qiskit metal. One of the tricky things about flip chip is that the meshing that you want, it's not just determined by the chip that you've drawn, it's also what is going on the other chip that sort of faces this opposite, right? I mean, if I have some really important feature on my cap, I probably want good meshing on whatever is underneath that, even if maybe it's not generically or naively such an important component. So this can be really tricky. I mean, we use ANSYS HFSS. We find the adaptive meshing works really well. I'm very interested to hear what people have done with AWS Palace and with some of the open source meshing software. I'm really excited to hear about any sort of success stories there, because it is non-trivial, but yeah.
How much do you find that material modeling plays a role in 3D models? Aluminum KI is low, but in flip chip, due to the concentration of field on the surface, does it begin to play a role in its taken into account?
You're always going to get better modeling if you account for like kinetic inductance. I'm not sure I understand the comment about it being more important in flip chip, but yeah, I mean, yeah, you'll certainly get better models if you account for that, for sure. Oh yeah, okay, this is sort of a trivial point, but if you are doing electrostatic simulations like Q3D, I think the only sort of new step is you need to make sure your grounds are united. It's kind of obvious, but yeah. And if you're doing driven eigenmode, I mean, there's basically no difference. But by and large, the meshing can be more tricky, but I think there's not really any fundamental differences. That and you now need to do a little bit of like 3D drawing as well, which is maybe not always easy. Yeah.
Is there any value in the workflow where you kind of simulate one layer and then the other?
I mean, this might depend, maybe, but not if your layers are really tightly coupled with each other. So yeah, I mean, it's certainly maybe worth a shot, but I mean, we're interested in things like how strongly coupled is my charge line to my qubit, and so there, and also, I mean, this ends up, if you've metallized your cap, that ends up being a really large, a factor in how E fields are going to, spread out. So I find I don't really think you can get a particularly good understanding of things if you've like left out one chip entirely. Okay, so actually, I mean, this is sort of all on flip chip for now. Any other questions or yeah? Okay.
Do you always include the indium bump bonds in your simulation? Did you finish it at frequency or any other relevant parameters?
Oh, well, I mean, it's what gives you a galvanic connection between the two, so that's super important. So if you have like no bump bonds, then you're not at all going to be, doing things physically correctly. So yes, yeah, absolutely. I mean, whether or not you include like every single one of them, especially if you have like a grouping, then I mean, maybe not. But I mean, make your model as accurate as you can. So if I mean, the bump bonds are lithographically defined. So if you know where they are, then put them there. Oh, sure. Yeah, of course, yeah. Okay. So moving on now to flip chip. So what is the point? Or sorry, not flip chip. Chiplet. What is the point of chiplet? Okay, so this is like a very old Rigetti device. It was 80 qubits, 80 readout resonators. So 80 qubits with squids, so that's 160 Josephson junctions. These are just fixed couplers in this chip. So when you think about something like yield, right? So if you're a new grad student, doing fab, maybe you don't follow the resist recipe great, your yield's like 5%. Okay, that's on you. Even if you're really good at what you're doing, I'm totally not speaking from experience there. Even if you're really good at what you're doing, your yield is north of 99%. And some of this yield issues are just going to be like systematic, right? You get some percentage of just issues with a batch. But you also just get random errors, right? And so, 99 point something percent to the power of 160 or to the power of 300, is actually already not looking so great. And so if you can sort of get away from this issue, or, if you try making a chip like this, even if you have a really good process, your junctions yield a very high percentage of the time. The percentage of the time that an entire chip will have all yielding junctions is not going to be nearly as high, and it can still be really challenging. So the solution is that, or a really nice solution, is that you can break your silicon die up into multiple dies, so to really have multiple different chips. You only need to get all of the junctions on one chiplet at a time to yield, and then you can combine them together. Of course, combining together is quite non-trivial, and we'll talk about that later. But this ends up really making things easier from a fab perspective, and really ends up improving your fab yield. It kind of ends up helping the fab team a lot and putting a lot of challenges on the design team, which is sort of what makes this challenging. But it does really help a lot from a fab perspective. This is not a completely outlandish idea. I mean, for sure, it's challenging in a quantum computing perspective, but this is used very much in like the world of classical computing. I believe GPU manufacturers do this quite a bit. Maybe you could. I don't know if you'd want to, but frankly, actually, I don't have a confident answer to that.
Benefit from the chiplet architecture a lot, and so you have to characterize the chip fold before knowing it's actually one that yielded.
Right? Yeah. So that's a great question. Oh yeah, okay. So the question was, if you really want to know that things have yielded well, you want to test it at cold, right? Like, I mean, you can do some testing at room temperature, but ideally, you'd really like to test things at cold to see that you've actually yielded, and then you can have confidence. So yes, the bump bonding, I don't know that that's going to be reversible, but the compliant interposer, that is reversible. So yes, once I've bonded a cap onto a chip, actually, you know what? I'll answer that on the next slide because yeah, that we'll sort of get there in a moment. But you already end up getting a huge step forward if you can just do room temperature testing, right? At the very least, there you can check for shorts and you can check for opens. Also, one of the things, well, and also you can test that your junctions turned out where you want, right? You can do, the Embagog-Barberov relation. You can figure out, okay, you don't necessarily only worry about shorts and opens. You might worry about like this junction resistance is way off from where I wanted it to be. But if you can learn all of that at room temperature, then you're already way, way, way ahead. Of course, some like unfortunately placed TLS, you only learn it cold, but that's, yeah, you're already 90% of the way there if you can do room temperature. So then sort of the dream for this is that it's not only, actually in this architecture here, so these are the qubit chips, those are chiplet, and then the cap chip, here that's still monolithic. The dream though is that you make both of those chiplet, and you just have a single carrier wafer on the bottom that's going to be monolithic. Because the thing is, junctions have, a certain yield, but also some of these 3D signaling components have, only a finite yield. And if you're using a via to deliver your signals, then a failed via is also just a failed qubit. And so that's also some number north of 99%. You also usually have more, well, probably around the same order of magnitude of vias versus junctions. So that's also something you very much worry about. So the dream is that you also have your cap in a chiplet architecture, and then so this is a carrier that we've done before. So you of course have holes in the bottom for both mechanical stability and thermalization. And so now you can both swap out your caps and your qubits. So you don't actually need to be able to reverse the indium bonding. If I just say, okay, if I get a qubit chip that yields and a cap chip that yields, as long as I can pull them in and out of this carrier, as long as that can be reversed, then if either of them fail, I just throw away the pair, and at least still you're only throwing away pairs instead of throwing away a full 1 million qubit chip or whatever scale we're thinking about right now.
Are they already bonded? They throw away the pairs, so the signal chip and the bonded?
Yes. I mean, the cap chip and the qubit chip, those are bonded. Yeah. The carrier, I actually am not certain if the idea is you bond them to this. I don't necessarily think you would. I'm actually, I can't answer that with confidence. But I don't think they are, would be my guess. Yeah. But for sure, yeah, your qubit chip and your cap chip, those are bonded, of course. Yes. Yeah. Is there anything else to say here? Yeah. Okay. Okay. So, yeah, question?
How do you move the chipless once it is bonded?
Yeah. So I think So the question, is reversible. I can't answer that with confidence, but I don't think it would work nicely. I would not want to do that. Okay, sorry. So this is maybe a nice time to pause already and think about what it's like as a designer to actually design for a multi-chip architecture. So for one thing, and this is more of a nuisance than like a real fundamental problem, but when you're simulating qubits on a chip, it might be nice to be able to sort of simulate some sublattice and say, okay, I'm now sort of going to tile this simulation result over the chip. This is a great way to save time. If you've broken your chip up into chiplets, then you almost have a chip that's defined by edge cases, right? You have much more perimeter per area, right? When you've broken things up. So this means you have a lot more edge qubits. And so this can be a little bit of a point of annoyance. It means it's a little bit harder to translate things. This isn't a fundamental issue. I'm sort of just expressing my own pet peeves right now. Another more important point, though, is that when you're designing a chip on a single silicon die, you'd probably like to just put a big buffer around the perimeter and say, okay, this keeps me away from whatever's going on outside the chip. I'm going to make this nice and large, and I don't have to worry about edge effects. But when you have to go from one chip to another, for one thing, you can't make that buffer region enormous because then that also is setting the pitch between your chip-to-chip qubits. So you sort of have to. Those are two competing design variables. So you have to balance the two. And then, of course, you also have to worry about whatever you have inside that buffer region, right? You're going to ultimately have signals going through there. So this now becomes like sort of in play for the design space. So you have to think about these things. The other thing is that inevitably, the qubit pitch when you're going from one chip to another is going to be a lot larger than the qubit pitch, inside of a chip. And so, if we're thinking about using some sort of lumped element coupler, this inevitably means you're going to have way more capacitance to ground. I think we all know here that capacitance to ground is usually a parasitic It's going to decrease the anharmonicity of any sort of qubit elements you have. That's not really so bad, but it's also going to decrease the coupling that you see. So this ends up being a bit of a parasitic that you have to account for. And so, one way that you might think to solve this is to use bus couplers, but it turns out that if you get really clever, you can still do this using tunable couplers, which I'll talk about in a moment. So this is maybe a good time to just sort of review what a tunable coupler is and some of the physics that comes up with them. So this sort of slide is all coming from a really nice work by Fei-Yan from the Oliver group. So a tunable coupler, the idea is that you have a transmon effectively acting as your coupling element connecting two qubits to each other. That's sort of the effective circuit diagram right there. And then the idea is that you can turn on and off this coupling. So by changing the frequency of this transmon that I have between my two qubits, I can increase the coupling strength or decrease it. And if you've got things balanced nicely, namely that you have both a capacitance or some sort of coupling from qubit to coupler, coupler to qubit, and also qubit to qubit, then there should be some specific parking point, some specific frequency you can set your coupler at, such that this coupling strength seen by the qubits goes to 0. And so this means that I have a coupling interaction that I can fully turn on and off, and you can do interaction. So I mean, this is very, very widely used in the community. It's a really great technique. Some of the important things to note here is that in order to get this 0 condition, you do need to have a direct qubit to qubit coupling, which sort of would manifest itself as a capacitance. Another sort of interesting point is that this 0 point, it always ends up arising with the coupler frequency above the qubits. So this ends up somewhat constraining how you can lay things out in your chip. And this is sort of showing here. So what you can actually think of it as is that the coupling interaction goes from like positive to negative, depending on which point you're at. And then of course, if you can move from positive to negative, there's a certain point where you also cross 0. Really what's happening here is there's an effective interaction that comes from qubit to qubit, qubit to coupler, coupler to qubit. That gives you one effective interaction. And then direct qubit qubit gives you a different one. And if the coupler is above the qubits, then these have opposite signs, and you can pick a certain point where they cancel each other. Some work that Rigetti did some years ago is looking at, okay, so let's suppose that your tunable coupler is a floating transmon, not a grounded transmon. It doesn't necessarily sound like such a radical idea right out the bat. I mean, we do floating qubits all the time. But it turns out that if you do this, you actually end up getting some very different physics. So namely, that depending on how you engineer the capacitances, you can actually have this 0 coupling condition arise either with the coupler above the qubits or below the qubits. You can get either condition. And it depends, you're like one per configuration, but depending on how you've designed the capacitances, you can get either. This ends up being really nice because it means that sort of generically, groups will usually put their resonators above the qubit frequency and their couplers above the qubit frequency. This has sort of a whole host of challenges from a frequency crowding perspective. It also means that the sort of like dispersive, the detuning from resonator to coupler ends up usually being smaller than resonator to qubit, which can be a challenge. So by moving the couplers below the qubits, you can kind of get away from this issue. I know there was a talk on Monday by Dr. Sank that showed that it's actually really nice to do it the opposite way from a reset perspective. But we found that you end up getting really, really far already just by getting the resonators and the couplers far away from each other on opposite sides of the qubits. Yeah.
So couplers below the qubits.
Yes. Or that's one way that you can do it. You can do either, but yes. Yeah. Oh, of course you have to worry about that. Yeah, I mean, of course you use like thermal population. Also, I mean, we do want these to be transmons, not Cooper hair boxes. So you have to worry about, if your EJEC gets too low. So of course, that is something you worry about, but it ends up like very manageable. Yeah. Okay, so I've sort of written out some of the physics here. This is really just showing you like kind of like the matrix elements of each transmon mode with the charge operator. And this is sort of showing how they combine together. Let's actually like, I want this to be a little more than just a talk, a bit more interactive. So let's actually go through a little bit of the physics here. Okay, so if we're thinking about the symmetric configuration, actually, I think I show both, right? Okay, yeah. So when you're picking whether or not your coupler frequency or your 0 coupling condition is going to be above or below, how you select that is by choosing whether or not you're going to do a symmetric or an asymmetric configuration. If you have a grounded coupler, you're kind of locked in at the asymmetric configuration, where this it would just be ground, and then I have my 2 qubits coupled to the same pad. So we call this the asymmetric configuration. And if you do this, the coupler's physics ends up being mostly the same, as a grounded qubit, it actually turns out that you can still get a zero coupling condition without having a direct capacitance between qubits, or sorry, a direct capacitance between qubits, which is nice, but by and large, the physics is similar. In this case, you actually get some pretty different physics. So here, you can kind of imagine I've got this floating qubit, and the floating transmon, and that is my coupler. And if I couple each qubit to different pads, then this is where I can get the zero condition where it's above, or sorry, below. And so actually just to go backwards a little bit, so to get this condition where these cancel each other out, it relies on you picking the signs of the detunings, and that's why it specifically has to be coupler above. So you can kind of like engineer, these terms are always going to be much larger than these ones. And if you sort of go into like the RWA, right, these are like the difference terms, or it's the Schrieffer-Wolff transform. These are like the difference terms, and these are the sum terms. These are always going to be a lot smaller than these ones. And so it's really a matter of engineering the sign of these such that these cancel out nicely. But it turns out that, so this is the equations for the charging energy terms in here. And namely this one here, I've left out E2C, but it ends up being the same. You sort of swap some of these indices. You get a difference of capacitances here. And so really picking between asymmetric versus symmetric is actually just a matter of picking one of these is going to be effectively zero valued, and the other one's going to be very non-zero valued. And that's basically how I can pick the sign. So I no longer need to engineer the frequency allocation of my qubits and couplers. I can now engineer the polarity of the couplings. So to actually, actually just go through the math. So this is the full capacitive network. Maybe, homework is write down the Hamiltonian, the Lagrangian for this. Don't do it. But if you do all that and you make a handful of approximations, you get these in the symmetric case. So of course, the trick to this is that a lot of these are zeroed, right? If we're thinking about the asymmetric or the symmetric configuration, then the coupling from here to here is going to be large, and here to here is large, but here to here is zero, right? And then that's sort of this whole game that you're playing. And so, if I've already zeroed out, the ones sort of corresponding to the symmetric configurations, and you can kind of see these have picked up, a nice set of signs, such that then when I plug everything in, I do the whole sort of transformation. So you sort of put everything into here, sort of solve for everything. You'll find that even when this has omega coupler less than omega qubit, this ends up still canceling out. And you can still get a zero coupling condition. Okay, probably way too much math for a talk. Any questions here so far? Yeah. Sorry, can you dynamically control it to make the? Oh, of course you can. Oh, yes. So I mean, this is a squid, right? That's controlling this. So the omega coupler, the frequency of the coupler, you have total control over that. And so this is how you can also do gates. By you're at this zero condition where the coupler is at a specific parking point. You can then move off that zero condition either up or down to get a non-zero coupling, and then you can do things like an I-swap gate or things like that. Yeah, yes, absolutely. That's central to doing gates with this. Yeah. Yeah, I will. So the question was, what sort of are some example frequencies that might arise here? I'll actually show some examples of this in a moment. Any other questions? Okay. Okay, so I will answer your question like 3 or 4 slides. One of the things that's nice about this, not just that you can move your couplers and your resonators on different sides of the qubits now, but some of this physics here ends up being really nice for doing couplings between chips. Probably the most important one is that you no longer require that direct capacitance between qubits, which is really nice if those qubits are physically far away from each other. Just a few nice properties to sort of think about here. You don't rely on that large on that strong qubit-qubit coupling. Another actually sort of niche point, I'll actually go back, is when you look at the charging energies here. Okay, so the charging energy of the coupler is set by the sort of total effective capacitance seen between the 2 pads, right? And so that's going to be given by the direct capacitance between these pads. But it's also going to be given, and this is true of any floating qubit, by the capacitance from, maybe it'll be nice to sort of show here, coupler to ground, ground to coupler, right? those sort of two add up in series and also give you another capacitance. Now this one's sometimes harder to control, right? You can't just get rid of ground, right? So this always sort of has some minimum value, and if if I want some size of my couplers, then I kind of can't control this entirely. So this ends up being sometimes a parasitic, where it's this really strong capacitance. It plays a big role in your charging energy, plays a big role in the coupling strengths that you can get, and you can't really turn it off. But the really nice thing about these floating couplers as opposed to grounded is that in a grounded coupler, the entire charging energy is just dictated by pad to ground, and that is strictly it. Whereas here it is sort of pad to ground, ground to pad, which means you have two capacitances in series, and if we just sort of suppose these are the same capacitance for simplicity, those get halved. So this means that when you do things in the floating configuration, the strength of this parasitic, which ends up being a really dominant parasitic, is actually halved. And you can kind of see that here. If we all remember the equation for charging energy, it's like E squared over 2C. If we look at the sort of components here, it's like, actually this one, sorry, I wrote this backwards. Yeah. So it's like the direct capacitance and ground, you can see, if you sort of pull the two out here, it's really capacitance plus half ground. And so just in general, this really nasty parasitic that's going to hurt you a lot ends up being halved in this configuration, which is quite nice when it becomes a dominant issue. So when I have these really large couplers connecting two qubits on different chips, the fact this gets divided by two actually ends up helping a good deal. There's a few different ways we can do this. Actually, do I have a slide? Yeah, okay. So thinking about how you can design things, when you're actually doing the connection, you can think about, okay, do I want to do things with a galvanic connection between chips? And then I'll have some sort of lithographically defined capacitor. Or you can do it with a vacuum gap capacitor. So that's sort of the two configurations here. So the way that you can kind of do this and the way that we like to do couplings between chips is you have a galvanic connection or you have some sort of connection from the qubit chip onto the cap chip and then back down again. So you sort of route the signal this way. Now you can do this using purely galvanic connections to move between chips, and then you just have capacitances on chip, lithographically defined capacitors. You can also, though, just directly use capacitances to move between the chips. So really, either of these work. I sort of thought it'd be nice to sort of discuss a little bit about the pros and cons of each of these. So if you're using a vacuum gap, that is a biplanar capacitor. Some sort of language that's good to know with flip chip is coplanar means you're on the same chip, and then biplanar means you're on different chips. So with vacuum gap, it's a biplanar capacitor or like a parallel plate capacitor, which we've all studied in basic E&M. So this means the capacitance scales with the area of the pads and inversely with the standoff distance. This is kind of nice because it means that you're not really very strongly tied to the perimeter of the capacitive elements, which is kind of great because we understand that having a low participation ratio with lossy dielectrics kind of also ends up scaling with perimeter. So you sort of escape from that design competition a little bit. Kind of a drawback of this is that vacuum has a dielectric relative permittivity of 1. So this is kind of low. It just means that it's a little bit harder to get really strong capacitances. And then the other sort of nasty issue to this is, as I talked about a little while ago, you are now relying on the alignment of your flip chip to get this coupling. So it's like the coupling strength between qubits now comes down to how well you've lined up these two chips. And so, I said earlier that you can get like really strong, really nice repeatability. If you want a really strong capacitance, maybe you actually don't want to put this in the etch layer. Maybe you actually want it to be like 3 microns. So, that's where like 3 microns with a 1 submicron variation, like that's, that's pretty variable. So that's kind of the drawback of doing vacuum gap. And then if you're doing things galvanically, then now you're kind of in a more familiar parameter regime where, you're doing all your capacitances on chip. This is kind of the generic scheme that we're all familiar with. So your E fields are mostly going through silicon. That means a really nice high relative permittivity. I mean, the nasty thing about coplanar capacitors is that the capacitance scales linearly with the perimeter, and it's actually like logarithmically with the standoff distance. So it really means if you want a high capacitance, you need to have a large perimeter, which I mean is sort of the design space that we all sort of live in generically. So you can get a little bit of a design competition there between variables. So yeah, any questions here? Yeah.
This is
I think my fab team would hate me if I proposed that. Sorry, so like flip chip here, chip here. Oh, interesting. That is interesting. Yeah. I don't know. Yeah. 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 Question.
increasing the vacuum gap capacitor actually causes some, dielectric material, maybe like, maybe the capacity may probably crystalline, but if it isn't, not sure how much of an impact will have. But I'm wondering if that could be actually a way to offset the distance between your flip chip and interposer, and also create a.
Oh, so it like uses the hard stop of sorts? Interesting.
Yeah, to probably distance that way.
Yeah.
And then, more defined capacity.
Yeah, you get like a larger dielectric. Oh, that's a very interesting idea. I mean, you need to make sure that whatever material you're using here both works nicely as a dielectric in the sense that it has a high permittivity and low loss and functions as a hard stop. No, yeah. No, these are all very interesting ideas. Yeah. That would be cool. Yeah. I think that eventually the community is going to have to start designing for flip chips. So I hope these are the kinds of ideas that people explore. Yeah. Any other questions? Yeah. For sure, I think that's something you'd want to worry about. Yeah. Like you really have to worry about everything. I mean, yeah, paranoia as an asset in flip chip design. Yeah. I mean, they're really, really small, right? Oh, thanks for the reminder. Yeah, so the question was, do you engineer these bonds to be well impedance matched? So I mean, these aren't transmission lines, right? I mean, they're super short. So I almost think of them as like a lumped element, connecting our transmission lines. So I don't really know that impedance matching is the right sort of mental framework. It's really just like making sure they don't have some nasty parasitic, which you do want to think about. Yeah, we don't find it's an issue. Okay, so I'll run through a little bit about experiments that were done here. So the other sort of configuration that we did sort of for experimental purposes is, what if you route onto a indium bump, come down into a routing chip? So this is kind of, if we go like way back, the third carrier, you can kind of have these like little edges that come up and sort of form this here. So they sort of end up creating like little placemakers, placeholders for each qubit. So anyways, so for this test, qubit chip galvanically connect to the cap, down to the carrier, back to the cap, down to the qubit chip. There's a lot of galvanic connections. So really, this is a way to sort of stress test that these indium bumps aren't causing us problems. So I'll go through some tests that were done to show that these things can work nicely, and also that we can actually hit this zero coupling condition in a variety of configurations. So okay, here's a picture of the chip here. So this one is looking at symmetric. No, this is the asymmetric with two bumps, sort of just showing that okay, as we vary the coupler flux bias, we can get can hit our zero G conditions and get really strong couplings. You do need to get sufficiently strong couplings. Qubit to pad, pad to pad, and pad to qubit. You need them all to be like sufficiently strong to actually both be able to get fast gates, but then also to be able to hit these zero conditions. You need to make sure that you don't have like some huge imbalance between these different parameters. Otherwise, your like zero coupling condition would be like really far away or way too close or something like that. This next configuration, so this is like the 4 bumps configuration, and it showing that it still works just fine. We can always hit the zero condition. This one's actually, I guess I thought, okay, I think I must have gotten rid of that slide. So sorry, I guess I'll just verbally answer the question about the frequencies. So often it's like 1.5 gigahertz is the, but between the coupler and the qubit. Yeah, I'll say 1 to 2 gigahertz. Yeah. So this one here is just showing that we could do a nice gate with this. So I think the fidelity is like, these are on 2 different chips. So this is a configuration where the signal is actually routing through 4 different bump bonds. I guess really you might say 3 different chips, or 4 if you count qubit chip, cap, carrier cap, qubit chip. And we got over 99% fidelity doing a gate with these 2. I can say as well, this was not just like a hero experiment. Like we do this regularly now. This system is like a core feature of our stack. I can't tell you in this exact experiment. This one was like a little while ago, but they're fast gates. They're not really any slower than our on-chip gates. They're quite fast. Yep. We haven't observed that. As it is, okay, so the question was, what are some the limiting factors of fidelities? Actually, I'm not on the 2-qubit gates team, so I can't exactly comment on this. I think in this particular experiment, I think they found that they were coherence limited in this particular experiment. If that sort of answers your question. As a designer, I worry about the parasitics and just like you do need to have fairly large capacitances to the qubits to get if you get a large capacitance to ground, that factor of 2 helps you, but it doesn't fully fix the problem. So it's tough to get really strong couplings to be able to do these fast gates. So that's kind of what challenges me, day to day with doing these. Okay, so moving on a little bit to another sort of feature of our stack. One of the things that works kind of nicely once you're doing flip chip is you can combine your DC flux and your RF charge line together. In this configuration, signals are combined at a diplexer at 10 millikelvin. This is just some data on that diplexer at the moment. And then you have a single line on the cap, which couples both your flux and your charge signals to the qubit. The advantage to this, one of the big ones is just that you have, sort of divide your signal lines by 2, at least below the mixing chamber. Of course, you still have separate lines coming down to the diplexer. And then 2 times less lines on the chips, right? You have 1 single line that's delivering flux and charge. So, it makes your sort of signal routing challenge a little bit easier. I should mention, actually, we weren't the first people to do this, but I think we were the first to publish openly on it. I believe Google's been using this since a little bit before we were. So thinking about how you actually do this on a chip, actually, so when you're actually doing this on a chip, when you guys are designing chips, I think it's probably sort of well known that generically you're going to pull your flux line or get your flux line a lot closer to the chip than your charge line, just because of sort of the couplings that you want. You want to mitigate Purcell loss in your charge line. Just generically speaking, your flux line is going to get a lot closer. That ends up becoming a lot less of an issue when your relative dielectric constant goes to 1 instead of to 10. This ends up dividing down the charge coupling strength by 10 and having no impact on your flux coupling strength. And so this kind of makes it a lot easier to get to get both of them into the same regime where you want roughly the same standoff distance. And so when you do things through vacuum, it gets a lot easier. I should point out as well, this is a hand-drawn picture, I apologize. Part of the nice thing about combining these lines together is that the RF behavior is kind of nice. So of course, when you're doing like DC or like, sort of megahertz frequency flux biasing, basically all the current is just going through this inductor here. This looks like a very large capacitor. So you just get a really strong flux. You don't really end up like driving your qubit at this megahertz frequencies. So that works really nicely. And then at RF, this effectively looks like a short circuit and almost no current is going through here. So one of the things you would worry about is like if I'm setting an RF signal down here, does that mean I'm also flux driving my qubit at RF? It works out that does not happen. And so this sort of circuit, this is of course a very crude model of it. This is like the first order approximation of what's happening here. But it ends up actually working quite nicely. It does mean that the physics of this coupling is a little bit non-trivial. It's not just a purely capacitive coupling for your charge line. You actually need to factor in that inductance. Keep in mind if this inductance were 0, and of course it is just like a small inducting wire and then shunt to ground, right? If this were 0, of course you'd never get any charge coupling because you just never get a voltage here. So the impedance of this inductance seen at your qubit frequency ends up being important for your coupling. So you have to sort of think a little bit more about how things are going to work. It doesn't end up just becoming a capacitive network that dictates your charge driving. So these are sort of some of the things you think about. Any questions here? Yeah, so the question was, do you have to think about loss, with the fact that your flux and your charge line are at the same distance from the qubit? This was absolutely. Just like how you have to think about the Purcell loss induced by your charge line, you have to, have the same sort of configurations here. It's just harder. It's a little bit more non-trivial. You can't freely move the charge line to whatever you want. So I mean, in the circuits I've been showing here, we're using floating qubits, kind of like the symmetry condition you aim for. But now you need to both balance the symmetry condition with making sure that whatever this inductive loop is, it's going to line up nicely with my squid and still get a really the ability to do, flex tuning without sending a crazy amount of current into my chip. So yes, absolutely. The problem kind of gets at least 2 times harder. 2 times the variables to think about. I mean, we're certainly experimenting with different gates. So in the chip we actually most recently deployed. It's on the cloud. You guys can use it. It went up at end of December. So that one's using iSwap gates. So yes, yeah, fast flex pulses. Yeah.
Sometimes want to attenuate those. And I was wondering whether the Skyflexer design can be where you have you split up the flex line in parts where one part is the RF line, and you can attenuate those differently. So the reason is that the C line will always carry some constant bias, right? And so if you have a lot of attenuation on that line, right, that's failing. But a flex line, a fast flex line, might be a noisy port, and so you might want to attenuate that a lot. Not as bad to attenuate it a lot because you're only sending pulses. Right, so in principle, you don't want to just start the drive and the flex line system, but also 2 parts of the flex line. So maybe you want to send your drive design like 3 lines with charge, flex, and fast flex.
Yeah. Okay. I'll attempt to repeat that question. For the online audience, the question was proposing the idea of splitting up the sort of what I've called the DC flux line into a true DC and then a fast flux, which is kind of like hundreds of megahertz frequencies. I think that's a really interesting idea. Yeah. Yeah. No, but a very interesting idea. Yeah, I can absolutely see some benefit in doing that for sure. Yeah.
I was wondering what would these equations even end up looking like? First order usually would just use the Maxwell equation, see what is the capacitance for my drive line and what is the conduction for my drive line. Now you have to sort of do both. What would these equations even end up looking like?
I mean, we've done like lumped element modeling to sort of get an understanding of how it's going to scale with frequency and things like that. I mean, it's not that hard. I mean, this circuit already is like a pretty good approximation. So another exercise for the viewer. You can just, Oh, yeah. I mean, there's nothing about this that would make it more quantum mechanical, for sure. Yeah. Actually, in the second half of this talk, I'll go into a little bit about how we'd like to do this modeling. And it does certainly help to have a bit more of an agnostic view of the circuit, since a lot of literature sort of thinks about like, okay, so we have a capacitive coupling, and it's an open circuit here. This would be like non-existent. This would be open. So for sure, you're kind of outside of that space that we more traditionally think about. So it does become non-trivial. There's nothing that makes it any less classical than a purely capacitive coupling, though. I will say that.
The physical footprint of the flex line, do you have to make up for the small inductance for making the switch?
Oh, interesting. Yeah, for sure, that's something you have to think about. Yeah, for sure, it's a little bit trickier to get to get the field that you want out of this line. And you have to figure that out. Yeah.
Yeah, I guess by extension to that, so that question was about you have to make the squid larger and that it plus noise and there's also pros and cons. And so I guess can you expand on exactly why it's so important to you to do it? Was it purely about real estate or are there other bonuses?
It's mostly a real estate thing. Yeah. I mean, half the lines is really important. If we're going to 1 million qubits, like 1 million coax cables is like, I don't know. If I can divide that by 2, I'll take it. And it's like this is not a fatal issue to design around. Like for sure, it makes things harder. For sure, it can, if you're not careful, introduce some more noise channels. That's absolutely something you worry about. But dividing the amount of signaling in half is a huge benefit, for sure. And keep in mind that if you have a flux and a charge line, that is still 2 per cell channels, right? Not designing them so carefully. I mean, I guess when you short the flux line, it should be a very weak per cell channel. But yeah. It should be pretty negligible, but it is also something you have to think about. So yeah, it's not a total loss. Another question?
Yesterday, that for the flux line, even though it's shorted, it's not capacitive to coupling to your qubit. There are like significant Q1 decay channels through the flux or through the record coupling that, if you're not careful, can be quite high. This is going back to Ben's controversial hands-on paper. There's like both M and M prime coupling.
Yes.
Driving common current in your switch loop. And what we typically think about sort of tuning the frequency, that's only differential coupling.
Yep.
That's what we call M coupling, right? But you also need to simulate the M prime coupling that can also delta K channel.
Yeah, that's a very interesting idea. Yeah, I have not myself thought about that a whole lot, but that's a really interesting point.
Yeah, we essentially like we ran into this problem where flux line was visiting our grid and simulate with the M coupling, not the M prime coupling.
Interesting. Interesting. So so that's entirely it's the common mode. I see. Yeah.
Inductive effect, and you don't have any capacitive component there. You're not capacitive to sell off, but very inductive.
Very cool. Very interesting. So to repeat the question, it's the fact that when the current in a squid, there's not only the differential mode, but there's also a common mode, and through flux coupling, you can get coupling to either mode there. And so, just thinking about how that impacts T1, and I think that's a very interesting point. Yeah. Okay, how am I doing for time? Oh, okay. Yeah. I was sort of going to divide this into 2, but I think this is a more interesting talk, so I'm trying to eat into the second one. Okay, so I thought I'd finish off the sort of first half of the talk with a little bit of thinking about sort of these specific 3D integration components and sort of how they form a bit of a toolbox for a designer and thinking about using these tools and the things you need to keep in mind. So one of the really important things that we have at Rigetti are superconducting through silicon vias. This is really central to being able to do the 3D signal routing, be able to send the signals through the cap chip. I should point out, this is a figure from 2017. These are 8-year-old CSVs. But anyway, so one of the big things you have to worry about is that if the scale on this is like hundreds of microns, this is a big capacitance to ground. So you always want to be accounting for that in your simulations, sort of in your modeling and your predictions. This is one of the big drawbacks to using this sort of circuit element for anything. The other kind of clever thing that you can do is, we talked about how the cavity sort of forms like an electromagnetic caging around your qubits. You of course also have to worry about how are the fields going to be propagating throughout the silicon. So a classic technique from sort of classical microwave engineering is via fencing, and that if I can put metal posts all throughout my dielectric, inside the dielectric, then that allows me to sort of contour the E fields and constrain them. And so that's also something that you can, of course, do when you have access to through silicon vias, and it is a really important technique to leverage. And I especially think, I'm very interested. This is where I think it'll also be interesting to have sort of conversation here today. Sort of interesting to think about the new ideas that the community can come up with and explore. When more people in the community are using TSVs and this becomes a widely used technique, because it is really important for classical microwave engineering. You talk to any microwave engineer, especially because they use microstrip technology, the TSV is a central piece of their toolbox. And so a lot of classical microwave engineering is sort of done with TSVs in mind. And so I think that'll be really exciting when the community at large has this in their toolbox. Yeah. I can't give that detail specifically. Yeah, sorry. But they are, it's somewhat unrelated comment. They are superconducting all the way through. It's not necessarily easy to do, but it is something we were able to do. But yeah, sorry, I can't speak about the specific dimensions. Yeah.
So these are also really useful to break up modes that can arise in your chip, especially as you make it bigger, because when you make the box bigger, you have lower frequency modes.
Yep, for sure.
I was wondering, how do you deal with modes that arise in this package itself?
itself will also, as you make like the chips bigger and the packages bigger, then they also just have a larger vacuum space in which you can have modes. And I don't know if you can put keys.
Yeah.
Larger packages.
Yeah, so the question's asking about how you break up sort of chip modes through the vacuum in an increasingly large device. This is where flip chip helps a lot. The fact that I don't have this really large vacuum region. And when we're doing this etch into the cavity or into the cap, we're only doing it in certain regions where we've wanted to, right? So it is actually a standoff of 3 microns in some areas, and then it's close to 30 microns in other areas. So by leveraging this ability to change the topography of the cap, you can like entirely control that. So that part actually ends up being fairly easy. I might say that the box modes of the substrate are a little more tricky. Another kind of clever thing is that when you have access to flip chip, you can almost make, I actually don't know if there's a name in the community for this, but I've been sort of thinking of them as like flip chip air bridges, right? Where I can sort of come through, go up through a bond, maybe here I don't etch away, so it's just 3 microns up and then come 3 microns down again. It's not easy to have super tight pitch in your bump bonds, especially, and it's also especially difficult to like, have like an unetched region, then etched again. Like, the spacings here are difficult to work with, but you can actually get something that's, the geometry ends up being not so much larger than what you have with airbridge. At least it's a lot closer to airbridge than it is to wire bonding. So you can kind of end up sort of leveraging this in a really nice way, which is really good for CPW2, where you want to have good shunting between your ground planes.
How much does fencing increase the benefit from reducing crosstalk versus adding another potential interface that the mode participants into loss? Is the trade-off?
I mean, it should be weak. You're putting these like around sort of the outside of the qubit, so this shouldn't end up being like a dominant contributor to the charging energy. I don't have a great answer for like exactly how much you gain and lose, but that's not something I'd worry about too much. Okay, sort of the last slide I have in this presentation is looking at our the chip of the future. This is our 36 qubit device. We've set getting one of these working with nice fidelity as our mid-year goal for 2025. So this one is where we have 4 9-qubit chips all tiled together. We've demonstrated really nicely in the past 2 chiplets where you sort of go between the 2. It ends up being a completely different challenge when I want to have these like nice connections here to here, here to here, and then like here to here, right? You need like the alignment, you sort of have a whole extra dimension of alignment. But so far we've been testing these, we have a few cold right now, and that we're really excited by the results. And so, we look forward to presenting these to the world quite shortly. Yeah, so that's all for sort of this half of the talk. Yeah, I mean, it's yes.
You guys want to take a small break?
Yeah, with 5 minutes we'll reconvene. Yeah.
We'll just take a quick 5-minute break. We'll be right back.
From what? Interesting. Oh, I said yeah. Like the sort of like hands. So yeah, that's cool. Yeah. That's a fun comparison. Sure. Oh yeah. This is all in the paper. You can read this on that. Yeah. But so I had like several slides. Which ones?
One with G equals to that one.
Yeah.
So in this case,
this is just a generic. You'll find this on a tunable coupler paper.
Yeah, but you say that the frequencies are omega-1 and omega-2 higher than omega-c?
Yes.
So this.
The key thing to note is that G's are not positive. This one is positive and this one
negative. You wrote. They have the same sign. I don't care about.
Oh yeah, sorry, you're right. Yeah. Okay, yeah. So the same sign. Yeah. And then.
But the multiplication will be positive.
Yes, same sign. So this is positive. Coupler is smaller than omega-1 and omega-2. So these are both. Hang on. Let's think here.
So this would be negative, and this is the dominant part. So I don't care about this.
Yeah.
So this is negative. Negative. That's positive. Negative. Isn't it negative? Isn't it positive? And then G12 is negative.
Oh, sorry. Yeah, G12 is negative. Yeah. There we go. Yes, G12 is negative. Yeah, it's a lot of sign accounting. Yeah, it's really easy to miss a factor of -1 here. I just made the mistake myself. But yes. So it works out. Yeah.
Hey, how's it going?
Hi.
I'm Stefano, and so I don't work with superconducting resonators, but I do, or like superconducting qubits, but I do superconducting resonate for like dot freedom.
Oh, interesting.
And I also use HFSS. And it's like a lot what I do. So I kind of wanted to ask you some like, question about HFSS. Is that something you do?
It is, yes. That's what I use. Yeah.
So you use the superconducting material. Do you just use a PEC, or do you consider the kinetic inductance as an impedance sheet? How do you?
You can do either. Yeah. If you want to include kinetic inductance, I mean, kinetic inductance is very low. If you're doing like the CPW, it ends up being like 1% or less, sort of compared to inductance per length compared to just like geometric inductance per length. So you actually can get away with not using it, but for sure, yeah. So yeah, you can do it's like a complex conductance, and then that is effectively complex conductance is effectively like nanohenries per sheet.
Yeah.
So
you do like the impedance sheet, like surface.
Yeah, that's how you can do it.
And then,
I mean, if you're doing something like titanium nitride, then like you really need to worry about that because it's huge, right?
Yeah, I guess we use niobium.
Yeah, so that's it. I mean, it also depends on how you grow your films. If they're like super thin, you get a different kinetic inductance.
Yeah, so we have like 100 nanometers.
Oh, it's fairly thick. I think it's
fairly thick.
What is it? Is it the London penetration depth or the coherence length that needs to be longer than?
I'm not sure. This is all like no one talks about this.
Okay, there's lots of literature on this. I wish I had like a reference to hand you off the bat, but there's.
So what would compare to the London penetration depth?
And the coherence length, and it depends on if your thin film is thicker or thinner than that. You get sort of different regimes that matter for your kinetic inductance. I was like doing an estimation like 2 weeks ago. I'm embarrassed I don't remember it now, but yeah,
okay, I'll definitely look
there's lots of literature on this.
And then my other question: talk about uniting grounds.
Yeah.
Do you do that like through the via, or do you have like some?
So if it's electrostatic, it doesn't matter how far away. You literally just need a PEC connecting the two grounds together. Yeah, if you're doing like a Q3D, right? Yeah. So it's pretty trivial. Yeah, I mean, it can be as simple as like if you're an HFSS, just like draw a cylinder, and because it's DC, it doesn't matter how far away it is, right? So it's I got specifically questions about like how do you change your models, to do this. Oh yeah. So for that one, I mean, that one. The best practice is just include every geometry as accurately as you can. So, I mean, we are uniting grounds literally with bonds, in specific locations. So the best bet is to do the same thing. Yeah, thank you. Oh, thank you very much.
Two different qubits. You find one software like a one die and two different qubits and two different chiplets.
Yes.
You do some sort of cross where you can.
I think for sure you could.
Yeah.
Yeah, absolutely. And then you don't have to worry about like the parasitic. It's just yeah, absolutely. I think that's a great idea.
More than one qubit.
Oh,
that's what I'm getting at.
Oh, interesting.
So you could like couple together, like two qubits in one chip, two qubits in another.
Interesting. Yeah.
Well, maybe it's not.
No, that does because I think there has. I can't recall the groups, but I think there have been groups that have sort of shown there's like many to many. Of course, you can like turn them on and off. Yeah, no, I think that's a very interesting idea.
Okay.
Yeah, and there's nothing fundamentally about this that would mean that you can't do buses, right? With like galvanic connections, like I absolutely think in principle that works. Yeah, of course. Oh yeah. I think my second talk is sure. I think we'll start. Thank you very much. Yeah, thanks. I'm going through the way we've been using S matrices to pull out loss rates and sort of, yeah. I think it's less interesting than the first half, hence me not being concerned that I've gone way over.
I have some more questions about your company.
Yeah. Of course.
So thank you. Very nice talk.
Thank you.
I think we met the
Yeah, of course. Yeah.
So kind of starting my lab, and actually one of the things that before actually coming to academia, I did a brief stint in industry and worked on microwave circuits and
very nice. Yeah.
things like through vias and doing passive components and alumina.
Mhm.
So we made these like thin alumina that were very like 40 micron thick, and then we used them for various passive components for recording. It's also a research division for a couple of years, or I switched back to academia.
Yeah.
But the reason why I mentioned that is because even though I feel like a lot of people in the field still think as a physicist, and I'm trained a physicist, but we don't necessarily think about scaling and all the challenges and engineering challenges. That was really nice to hear.
My personal belief, and it probably this is because I'm trained as an engineer just as much as a physicist, but I really believe that at a certain point, superconducting qubits, especially if you're doing like transmons and dispersive readout and so on, it's like 75% microwave engineering, 25% physics. It becomes more of an engineering problem than a physics problem.
That's kind of actually where I want to take my group. So one of the things we want to work on is exactly comes like scaling signal lines.
Very nice.
I have some ideas for flip chip packages and so on.
Oh, that's awesome. Yeah.
So we should definitely stay in touch.
For sure, absolutely. I can like give you my email or I'm gonna on my slides.
I'll connect you over LinkedIn or something.
Yeah, of course.
We'll talk more.
For sure, let's do that. Yeah, I'll start the next talk. I actually don't think it's going to be very long, so I think we're doing okay for time.
Okay, online, we're starting again.
Okay, we'll start the sort of second half of the talk now.
So quick announcement. So we will send another link or sort of another email to all of you, which has two links. Technically, you guys only care about the in-person stuff, so we have sort of a response form where we would like to get all of your opinions. What you like about this, what you didn't, content-wise, right? It's just like sort of feedback for us so that we can know for next year how to improve, what to remove, who not to invite. Just kidding. But all of these things, so you get that right away. Food's here, so pizza today, which is lovely. And then again at 1 p.m. right, there's Keysight, 30 instruments, quantum machines, right? They'll be here. Talk to them, do whatever you want, and then at 2 p.m. right, we'll follow back. Yeah, second talk now, second part. Let's give it to the speaker again.
Okay, I'll try to be quick. I'm sure everyone's salivating, and I'm on a clock. I recognize. So the second talk's a very different topic. I sort of thought it'd be nice. This is a little more of a workshop. Sort of just looking at this nifty way that we've been doing loss modeling, which we find works fairly well in our kind of non-trivial and especially densely integrated environment. Sort of discovering Purcell channels that maybe you thought you had dealt with and then realized afterwards you absolutely did not. So yeah, it's sort of just a nice trick that we've been using, and I thought might be interesting to share with people. There's a sort of a fun little derivation for it, which I thought would be good to run through. Okay, so just what we'd like to learn about our QPUs when we're doing this modeling. Of course, you worry about parameter extraction and circuit solving, and then you also worry about a sort of continuum coupling. So you can sort of think of this as just modeling per cell loss, although of course these things always are a two-way process. So the extent to which you have per cell loss through your charge line is exactly also the extent to which your charge line drives your qubit. So sort of it's a one-to-one mapping. Yeah, so this is sort of what you think about. There's a lot of different ways to do these simulations, and I'm by no means saying this is like the best or this is going to replace all or even any of the tools that you already have in your toolbox. But again, this is the one that we've been using for a little while. We're kind of happy with it. So sort of a wish list that we would have for our simulations. We'd like our simulations to be accurate. If they're not, then why are we even doing them? We'd like them to be scalable. So we'd like our method to work nicely on a system of large size. We're not necessarily going to be running a million qubit simulations in HFSS, but we'd like to be able to do 10 or 100 and not be stuck at like 1 and 2. It's nice if our simulation and subsequent calculation methods are general. If we don't have to make certain assumptions about what is the coupling circuit that we're attaching to a given port. If we can just sort of be a little more general about it. We'd like it to be extensible in the sense that if I run a simulation, I get some information about the system. It'd be nice if I can say, okay, what if I tweak this parameter? Does that mean I have to go back to the cluster and run for 12 more hours, or does that mean maybe I can just change something, make a small change after the fact? It's certainly nice if it's extensible. Hopefully they're insightful in the sense that it doesn't just tell me, okay, this is your T1. I mean, if I had a sort of simulation system where I could plug in any GDS and it would just instantly tell me T1, that's not bad, but it would also be nice to know, why is my T1 not what I'd like it to be? It's good if it provides some insight. And this is where things like plotting fields helps, and we have tools for this. And we'd like it to also be complete. I'd like to be able to hit run in a simulation and then learn everything I'd like to know about my chip. So not just T1, but also, what is my qubit frequency? What are my couplings? All of these things would be nice. I don't really think there's a single simulation method that checks every single box here. There are, of course, some really powerful methods, that we heard about earlier. Here are just some of them: energy participation ratio, the sort of circuit synthesis methods. I think specifically of a paper by Solgan, DiVincenzo, and Gambetta, which was a very nice paper, and sort of black box quantization, which of course some of these are actually built on. I think all of these methods actually check like almost all of those boxes I just had up, and maybe you could argue check pretty well all of them. But I don't think that any of them satisfy every single item on our wish list perfectly, nor does the one I'm about to talk about today. But again, I sort of hope it's maybe a nice little tool in the toolbox. Okay, so the assumptions that I'm going to be making today is that our passive network, so what we're going to be simulating is leave the qubits out of the simulation, or leave the junctions out of the simulation structure. We're going to just model the passive network, so the actual 3D structure. Again, this method I think becomes a little more valuable when you're doing things in a 3D environment and you have lots to account for. So we're going to assume that this is lossless. That is certainly quite an assumption to be making right off the bat. Assume the dielectric loss is 0, but it does make the math work a lot better. We're going to assume the network is reciprocal. I think this is a pretty safe assumption to make, but yeah, there's no circulators inside of our chip or no nice non-reciprocal elements. That helps a lot with the math. We're going to assume that our qubits are well approximated as linear elements. This is also, it's a controversial assumption. It's not bad in the transmon regime, especially because what we're going to be looking at is continuum couplings. And so as long as the loss and the coupling is well described as a single photon exchange, then even though our transmons aren't actually perfectly linear, it's not really still a bad approximation. I haven't really thought about how this model would work if you tried to use fluxonium, but my first guess is that it wouldn't work very well. So this is also certainly one constraint we have to place on things. Oh yes, and then this is not an assumption, but it's an important housekeeping element. Because we're going to be modeling our transmons as linear, we all, I think, know here that the equation for the frequency of a transmon is not omega equals 1 over LC, right? The fact there's 0-point fluctuations means that the inductance that we write down from the Ambergwalker-Baratov relation is not the same as the sort of effective inductance that you would need to set a harmonic oscillator to get the same property. Like certainly to first order, it's very easy to calculate them, and even to nth order, it's not hard to figure out what the effective inductance is. But that's sort of just an important housekeeping item. The actual JJ inductance is not the same as the sort of linearized inductance. Okay, so I'll sort of start by okay. I'll actually make a brief comment first. I'm going to use quantum network theory and sort of quantum optics to do this derivation. Sort of the skeleton in the closet of this is that there's actually nothing quantum mechanical happening here. The first two slides are sort of starting from quantum mechanics, show that we can basically be classical, and then admit that really it was all classical to begin with. But so, in the language of quantum network theory, we can break up any traveling voltage wave into two quadratures, an I and Q. These are the expressions for a traveling wave. I and Q is kind of the sort of more electrical engineering language. X and P maybe is our sort of quantum optics one. You can write them down as traveling waves to sort of just parse this a little bit. This here, if you assume that you just have a single frequency, then this is basically just doing the Fourier transform on a continuum mode operator, and it's basically just a time operator. This is not for a photon, it's photons per second. So actually, maybe sort of raise your hand if you're familiar with like continuum quantum optics and like continuum operators of input-output theory. Okay, 4/2 of a hand. Okay, I probably should have thought of that before I wrote this talk. It's a way of so in a 1D continuum, you have an infinite set of modes, right? I mean, if you constrain a harmonic oscillator, then you can write down a discrete set of modes. But as you set this sort of like oscillator to think of like a transmission line, if you set the length of the transmission line to infinity, you now have infinite modes. And so this is a nice way of writing down. It's literally sort of thinking about like, yeah, take the limit as you go to infinity. And now you can't actually write down like photons in a mode because you have a not just countably infinite, but an uncountably infinite set of modes. And so you think about like photons per second or photons per hertz. So the natural description is photons per hertz, but then it's not hard to do like sort of Fourier transform to get to photons per second. This is how you think about photons traveling down a wave or voltage waves traveling. And of course, anyone who sort of does microwave engineering knows that this is sort of the language that we often like to use for microwave engineering, right? We don't just write down a voltage at a point, we write down a voltage wave traveling down a transmission line. And so it's really natural to also be able to use photons per second and think about photons traveling down a line. So this is a really important framework from quantum optics. So this looks really nasty, but really you can sort of just think of it as like photons per second. And then this is kind of like the 0-point fluctuations on that, which tells us now voltage traveling down the line. And then these two equations you'll notice are almost identical to each other. I believe it should just be a change of, I here and not here. Okay. Does this like at least sort of make sense, even if we're not familiar with continuum quantum optics already? Oh man, okay. I apologize. A question, yeah? Yes, so actually this operator right here is photons per hertz. If you pull this out, so if I say, let's just suppose I only have one frequency to worry about, you pull this out, you can actually see this is like the Fourier transform of that, and now it's photons per second. So really, to actually properly do like continuum quantum optics and sort of think about like these discretized modes, the best way to worry about this is photons per hertz. Actually, I mean, really the reason why you have to write this one in photons per hertz is that voltage, like the 0-point fluctuations of voltage depend on h bar omega. So you'll get different fluctuations for different omega. But of course, if we sort of think like, okay, my signal is 4.5 gigahertz plus or minus 0.00001 gigahertz, right, plus or minus a kilohertz, then you basically say my 0-point fluctuations are constant, and then this is just a photons per second operator. So yes, it has units of, well, it's the annihilation operator, so it's square root of photons per second. Loudon and Blow is a really nice reference on this. This is all sort of like foundational quantum optics, although again, I guess I'm remembering this is not a quantum optics audience, so I apologize.
The Atomos operator, it adds
a photon, yeah,
photon at that
of that frequency, yes. Yes, exactly. I mean, think about it this way. Let's imagine it wasn't an infinite transmission line. Let's imagine it was finite. I'm adding a photon in to a specific mode of this resonator, but now my resonator is infinitely long, and I have like an infinitely dense spacing of modes. Yeah, okay. I typed these equations out myself. There is some possibility that I made a mistake. Yes, there should be an I. There should be an I there. Yes, my apologies. Yes, there should be. My apologies. I want to point out. So I mean, this the whole like quantum optics formulation of this is not really necessary. I'm basically going to show that it's perfectly fine to use voltage waves, and then after that, it's classical. So if you're stuck on the first few slides, I promise you, like that's not so important. Okay, so a sort of trick that you can try is using like phasor relations. So if I have like the quadratures of the field, then and of course, we would like voltage to represent a real observable, but a sort of classic technique from electrical engineering is to write voltage as a complex variable, and then you can really nicely account for magnitude and phase all at the same time. So, there's sort of nothing about this that means that it can't work here. If you wanted to reconstruct I, you would just take v tilde dagger plus v, or minus of v tilde dagger minus v, and you can pull out q. So this is really sort of like a linear combination of these, using the complex number to get sort of the nice mathematical relations here. And then at this point, you find that the voltage phase in phasor notation is literally just a constant times the time operator. Oh, and here actually, I think, yeah. So here, this is where I'm sort of doing this, right? It's like pull out omega, say it's just omega naught, and now this is actually photons per second. And so we're going to work with that from now on. And then this is not a continuum operator. Subscript t means it's going to be per second. That's the notation I'm using here. So this is literally just still like 0-point fluctuations inside our cavity. Again, this is not a continuum operator here, so this is literally just voltage, but again, written as a phasor. And this is the last, more or less, that quantum mechanics sort of becomes required. Yeah, it looks like I need to brush up on my LaTeX skills. My apologies. Okay, so thinking now about microwave engineering. Okay, so scattering matrices are a really nice technique because they relate voltage waves in to voltage waves out. You can do, this is like the very natural language that microwave engineers like to use. It can, of course, be on a two-port network. That's a really nice model of things, but it can also be n-port. There's also a nice set of transformations that you can do, where you can transform into admittance matrices, which relate voltages to known voltages to currents. Take a column vector of voltages multiplied by the admittance matrix, get a column vector of currents. There's the inverse of that, the impedance matrix, which does currents to voltages, and so on and so on. These are a really nice technique in the microwave engineer's toolbox to be able to analyze arbitrary networks, be able to analyze networks where I can't nicely write down a lumped element description of it, but I can still fully measure and understand what its sort of behavior is. Maybe I don't have a super nice lumped element representation of it, but I do know something about it. And maybe I should also ask, sort of the audience, raise your hand if you're familiar with the scattering matrix. Okay, and raise your hand if you're familiar with like the different versions of it: impedance matrices, admittance matrices. Okay, yeah, I know that if you're in the basic session, you should know all this stuff very well, because I know that Lucas and David did a nice talk on this yesterday for the specific ABCD matrices, which are another formulation, although they only work with 2 ports. Okay, so there's a whole set of transformations that we can do here. And again, it's really nice to represent things from a microwave engineering perspective in the S matrix. The S matrix has a really nice property, or a few really nice properties as well, if we take those assumptions I started with at the beginning: lossless and non-reciprocal. Okay, so this is just the equation that I sort of had already. Outbound fields is just the S matrix times inbound fields. You can, of course, take the inverse of that. If the matrix is lossless, then it is unitary, which means the inverse is just the unitary transpose. And if it is reciprocal, then the inverse is its own transpose. This has the really nice property, I didn't sort of write it down here, but you can sort of do some substitutions, that if you sort of take these and sub it into here, you find that, okay, sure, so outbound fields is just S times inbound fields. Inbound fields is S conjugate, so which is really the same thing as saying S time reversal times outbound fields. So you actually find that if you do this, then you can, the S matrix kind of directly gives you both forwards and backwards equations. You could take a time reversal transform, because of course, time reversal is anti-unitary, so it's the same as taking conjugate transpose. And so the fact that the S matrix kind of naturally gives us both a forwards and a backwards relation kind of hints that it's going to be a really nice tool if we want to think in terms of input and output theory. Okay, so our system of interest, we have a set of drive lines. I probably should have not used the letter L, but anyway, a set of drive lines driving some scattering network. At the moment, we'll just sort of think about, let's suppose there's only 1 qubit of interest. So we have n ports, but just 1 qubit. These 2 equations here are literally just the first row of the scattering matrix, right? This is just the first row. It's saying like, sum up all the scattering elements times the inbound fields. I sort of set aside as a special variable the voltage at the qubit port. So we'll kind of say, this is VQ, and then this is like, sort of all the VLs. So this is literally just the top row, and this is just the top row having inverted it all. And what's sort of nice about this is that I'm not actually worrying about the entire scattering matrix. Just by taking these 2 relations, I sort of know everything. I'm taking all the information that the scattering matrix tells me about the relationship between the qubit and the ports. So at this point, I'm already kind of throwing away the relationship from port to port, because I'm not so worried about how much energy goes from my charge line to another charge line. I'm worried about my relationship between my qubit and these ports. We can do a whole bunch of rearranging. This is literally just algebra. Take the 2 equations I had earlier, do some sort of math, and you can pull out this expression here. really, it's key that I both had the forwards and the backwards equation. The fact that I had both this inbound to outbound and outbound to inbound relation, the forwards and backwards. And I can pull out now an expression sort of using the fact that a forwards wave and a backwards wave, you add them together, is the voltage at a node. So I can just pull out now just the voltage at the qubit, and it's sort of given by this sort of whole relation here. And what we'll kind of notice is that this already looks like a valid boundary condition in input-output theory. And so indeed, we can kind of substitute back in those like 0-point fluctuation equations we had to now say, okay, this is actually an equation I can write down in terms of like annihilation operators. And I'm really just saying that the annihilation operator of the qubit is given by annihilation operator, inbound and outbound, plus and minus inbound, outbound, times this sort of parameter here. We have phases that get pulled out. One of the key things we have to note is that these two equations here, these expressions here and here are just conjugate transpose of each other. So same magnitude, opposite phase. We sort of pull this out, and it looks a whole lot like a valid input-output boundary condition. We're just going to do a change of basis here to get rid of the nasty phase relation. So this is literally just redefining the phase of the continuum operators. This is perfectly valid. It's literally just a change of basis on these operators, only to make the equations look prettier, get rid of the sort of the phase shift. You'd want to account for this if I actually want to do some sort of like time domain reconstruction of things, but the physics is perfectly valid still. One more part of this that looks like quantum mechanics, although again, you can like basically swap with the commutation relation for, I can't remember what the analog is, but there's nothing about this is necessarily quantum mechanical, even though I've written it as such. So this is the input-output equation. Maybe a more common formulation is not summing over a bunch of these, but just having one loss rate, one loss rate. Raise your hand if you're familiar with this equation. Again, maybe you haven't seen it with the sums before, but yeah, okay. So this is, the input-output equation. Oh, well, this is really just a quantum Langevin equation. But of course, we're going to pair it with that boundary condition we had to make it an input-output equation. So this is, well, yeah, so it describes the unitary dynamics of an operator, really just like a Heisenberg equation. And then loss. Oh man, this is okay. I got to work on my latex skills. There's an A here. This is the dissipation, and then this is the driving from a bath. And so you can, and actually the original paper that sort of proposes input-output, they sort of show that you can prove that these have to be your dissipation has to like have this specific relation where like the drive term is square root of dissipation. And this one you can show that. This is required by making sure that the commutation relations of the field operators are preserved. Sort of like you can't have quantum noise shrink over time. If you had dissipation and no input, then your quantum noise would just shrink over time, and eventually you'd have like you'd violate Heisenberg's uncertainty principle. Okay, now that's the end of quantum mechanics for this talk. So one of the important things that Collette and Gardner point out is that when they sort of introduce input-output, is that if this is an invalid equation, then its time reversal ought to also be valid. So I'm literally just taking time reversal. Time goes to negative t, t goes to negative t. Time reversal is anti-unitary, so I goes to negative I. Loss stays the same. I guess I dropped the summations. That's embarrassing. Input goes to output. And so if we add these together, you can see the unitary parts are all going to cancel out, and it literally just tells us a relationship between sort of loss and driving. And this sets now the requirement that any input-output boundary condition must have to sort of pair in a valid way with a quantum Langevin equation. And you might notice that this already looks a whole lot like the form of the equation we had earlier. And so we can see that the electrical equation that we've written down is a valid description for input-output theory, as long as I can kind of reformulate things, as I sort of already have, into this expression here, such that it fits, with these loss rates here. And then I can say that, whatever parameter I pull out is a valid loss rate that actually describes the input-output relations, describing these continuum modes, interacting with my cavity. It is a valid boundary condition for input-output theory. This is the required form that it must have. I need to be able to write down my loss. Obviously, to derive this, you need to make sure you're like satisfying, Kirchhoff laws and whatnot to like actually pull this out. And then, if you can write it in this form, then that sort of directly tells you what the loss rates must be for input-output. So if we kind of just rearrange things a little bit. Oh, okay. This was going to be like 5 slides of math. I chose to just sort of like skip all of it. So you can kind of like show that like this is the requirement that your loss rates must have to both satisfy like the sort of electrical network theory we had, and also just like making sure that we satisfy the requirements for quantum Langevin equation. And you end up pulling out this expression here. I was really surprised when I saw that expression. I'm guessing that this is known in literature, but I have not seen it myself. But yes, if I write down a scattering, if I have a scattering matrix, I can, and I compute it for the full network, I can pull out the loss rate to any port just sort of from that expression right there. I'm 99% sure this has been put in literature before, but I have not been able to see it. So I thought it might be interesting. If I haven't seen it, I figured many of you haven't seen it, and I thought it might be interesting to share. This is a really nice expression. I mean, it's convenient in a lot of ways. For one thing, you can actually you don't even need to pull it out of HFSS and then do calculations on it. You can sort of write it in an equation and plot it inside of HFSS. So it ends up being very convenient. We like that a lot. It's not even impossible to put this as a convergence criteria because again, it's directly written in terms of parameters that HFSS can understand. And so it sort of has some really nice properties. Actually, yeah. So I'll make a few more comments on this. No, I'll make the comments later. Something that we probably ought to check is to make sure that this this whole okay, yes, sorry. So the one thing you'll notice is that I sort of magically say, oh, and this is the capacitance. How do we know the capacitance? We've known how to pull out capacitances since 2012. Black box quantization tells us how to do that. So this whole sort of theory is kind of built on top of black box quantization, where you kind of have to pull out some techniques from that and then have these nice ones on top. So yeah, this is sort of the expression here. So you do need to have, I mean, you can just do transformations from the S matrix to admittance, and then you get things as a function of frequency. You can take the time derivative. So that works just fine. You do need to, of course, have this as a sweep over frequency to be able to pull this out nicely. And then, that allows us to figure out the voltage 0-point fluctuations, and then that lets us finish the calculation. Okay, so an important question is, how do we deal with n qubits? I'm certain that there's a way that you could sort of formulate this, where you can fully deal with n qubits from the beginning. If you're familiar with the work from Solgan and collaborators, then you'll probably notice that a lot of the sort of formulation that I've derived at the end, while the equation looks very different, it ends up kind of being similar in theirs, where it lets you pull out a loss rate directly from these network parameters. And they actually do also have in there a nice way to do directly qubit-qubit interactions. So that's really, by the way, one of the major blind spots of this. It tells you loss rates, it tells you continuum couplings, does not tell you anything about the qubits. I'm sure you could extend it, but I have not done that. So the nice way that you can deal with qubits is by doing these port transformations, or these matrix transformations, where I can say, okay, so I'm going to use two properties. One of them is that you can generalize S matrices, where I write down an effective S matrix, where I change the characteristic impedance of the ports, and I can change it to a complex number. The math gets a little bit nasty, but it's totally doable. And then so I sort of renormalize it, where I assume that the characteristic impedance is not 50 ohms. It's either some different impedance, or you can actually set it to a complex load. And then you use a nice property that if you just cut out the row and corresponding column from an S matrix, that is the same thing as saying I assume all inbound fields are 0, which is the same thing as saying I assume it is matched by its characteristic impedance and that I'm doing nothing else to it. So you can actually just start throwing away rows and columns, and that's the same thing as just saying I'm terminating that port with its characteristic impedance. And remember, I can set its characteristic impedance to whatever I want, be it complex or real. And then this sort of gives me a termination. You might ask, why not just pull out the S matrix, load it into a SPICE solver, and then put in the terminations? And I don't actually have a good answer for that, except that maybe it's less interesting than doing it all with matrix theory. The astute observer will notice that you kind of have a division by 0 here, or at least it looks like you do, because I'm saying that for junction ports, what I can do is just set an inductance at the port, and then throw away that row and column. And it's the same thing as just saying, okay, this qubit is terminated by this inductance, and now I'm going to forget about it. I'm going to consider this qubit to be a part of my environment now. Of course, in this step here, we have to divide by the real part of the impedance. So it sort of looks like division by 0. I also can leave as an exercise to the reader. You can sort of show that when you actually do all of this, you never actually get a division by 0. It does not diverge. For all the terms that sort of seem like they go to infinity, it's an x divided by square root of x convergence. So as you set the real part of your junction impedance to go to 0, the off-diagonal terms also just go to 0 for that row and column that you're going to throw away, which is encouraging. This basically says that when I set the qubit to just be an inductance, there is 0 power delivered to that load, which there ought not to be because you can't deliver load to a purely complex impedance. So how you can use this in practice, and this actually really, I think, is the powerful feature of this tool, is that I can, after the fact, I've already done my HFSS simulation, I've already pulled out an S matrix. I can now set impedances, set inductances for all the qubits that I'm not studying right now to make them a part of the effective environment. I can now find an effective loss rate for the qubit I'm studying, but I do that after the fact. So I can choose the frequency of all of my qubits after I've already done my HFSS simulation. This means that, I mean, for one thing, if I've already, if my fab has already spent, or if my fab has already spent a bunch of time designing some cap structure, designing some 3D structure, maybe I can't change that anymore. I've got, an HFSS structure for that. Obviously, you need to do a separate one for every qubit chip if you're changing the metal layers there. And I can pick the inductances after the fact. It also means that I can simulate gates, right? So, this is somewhat of the limitation of the EPR method, where you put inductances on every port, and then that's it. So I've said that, this is the, frequency of all of my qubits, and now, that's it. The simulation is locked in. Whereas with this method, I can tune my qubits in the simulation. And it's not a matter of running a new HFSS for every frequency. It's actually just, I've already got my S matrix. I can, after the fact, sweep the inductance of some tunable coupler. So I can look at what is the loss rate of my qubit. Now I'm going to sweep the frequency of my coupler and see how that loss rate changes. And I can do all of that in a Python script that runs in milliseconds. Yeah. Yeah. Yeah, so I assign, the only thing that I leave out is the junction itself. Yeah, so all capacitance is all metal is still there. And you sort of have to follow like the black box quantization method to figure out what the effective capacitance is, where the junction would be. Put ports where every junction would be, and put ports where every drive line would be. And then I simulate this full scattering matrix. And then I can, using this technique here, set inductances on every qubit that I'm not studying at this moment, and find out what the effective loss rate is from this qubit, not just its T1, but its loss rate to every single port. And I can now play with the Hamiltonian. I can tweak the frequencies of the qubits that I'm not studying at this given moment, or even the frequency of the qubit that I am studying by changing its inductance. And I can find out how its frequency changes with respect to any number of parameters. And I think it is in a more complex environment where this becomes valuable, and especially when you have like really large connectivity, because you might say, okay, well, I need to do a frequency sweep here. So I'm already doing not just an HFSS simulation, but a simulation spread over frequency. But now I can vary every single qubit port. And so let's say I have 4 different tunable coupler frequencies I'd like to sweep over. That is a 4-dimensional space. I can do all of that in Python simulations that are literally just take matrix inverses. By the way, these matrices aren't large, right? If I have like 20 qubits, this is maybe like 50 by 50 matrix. Matrix inversion is in microseconds. And so all I have to do now is these little matrix inversions, and I can rerun the simulation effectively for every single parking point of every qubit, as long as I've done it once with a nice frequency sweep with the S matrix. A nice, oh yeah, sorry, yeah, this is supposed to be problem and solution, but I already gave both. An important test we might do is we better make sure this agrees with with black box quantization. So black box quantization predicts this, that the T1 is given by the capacitance over the real of the admittance. This is the total admittance. So this is sort of like after already placing 50 ohm channels on every port, what is the admittance? We can kind of still use this port subtraction technique, where we just put 50 ohm characteristic impedances on all the ports, throw away those rows and columns. I know that just directly pulls out this parameter that black box quantization tells us. And so, we get this gamma. We sort of just recognize from microwave theory that gamma is just the same thing as the impedance looking into that port. Again, after doing this sort of port subtraction on everything. And then another little sort of homework exercise that you can run through is showing that if I take these loss rates I've calculated, sum all of them up, do some sort of complex algebra, maybe throw back to early undergrad, do the math, and you can actually get the exact same expression that black box quantization predicts. So this is if I sum up all Purcell channels. Sum up all Purcell channels, I get a gamma total. 1 over gamma total is T1, and I get the exact same number that black box quantization does. Okay, so what does this give us? I do not think that. Yeah, sorry, question. Oh yeah. Yes. Oh yeah, sorry. So I'm computing the loss rates to every single port, and I'm saying that when I sum all of those up together, I better get the same answer as black box quantization, which treats just all of them as an environment. There's just all these ports make up a lossy environment. It gives a total loss rate. Yes. Yeah, exactly. Yes. Yeah. I mean, this is like, it's really nothing clever. I suspect if you ask any like microwave wizard, you know, that they'll tell you, of course, this is all well known. Because again, there's really nothing here that needs to be quantum mechanical. I know I baffled everyone with quantum mechanics at the beginning, but it need not be. This is just classical sort of microwave theory, but it works really nicely. It's very convenient in some ways. So, you know, sort of think about what this gives us. I do not remotely claim that this is a replacement for all or probably even any of the simulation tools already in our toolbox, but we have found that it's a pretty nice one. It's really easy to simulate sort of after the fact a whole variety of conditions of your quantum processor, you know, after the fact, especially if you have tunable elements. I think that's really sort of the use case here. If I have a quantum processor with lots of qubits and they're all tunable, and I would like to think about all sorts of different combinations of parking points, it's really, really nice to do that after the fact. And it allows you to sort of sweep a large parameter space with just a 1D sweep in HFSS. I can sweep, you know, my ND, you know, space of qubit frequencies. So yeah, so this method here, and I haven't tried this myself, but I don't see a reason why you couldn't combine this with the results from Solgan and collaborators to also then, okay, you've got this S matrix, convert it into an impedance matrix, and now they have a really nice method for pulling out qubit-qubit couplings using the impedance matrix. I do not see any reason why this would be incompatible. I haven't sort of looked into that myself though. And indeed, they also find a way to pull out the loss. So they also have a nice way to pull out the loss rates using the impedance matrix, but they do make certain assumptions about the structure of the port. So they assume that the drive is like a voltage source with a certain capacitive coupling, which is part of why, like, you know, in the first presentation, we show our flux lines just like this inductor. It kind of already violates that assumption. And you know, we need something a little more general. But this does not make assumptions about the structure of your drive port. It's just, it is a continuum. It is a one-dimensional continuum, you know, with some characteristic impedance, you know, coming into the port. And so, yeah, I think this part, oh, yeah. Also, when you're pulling out the loss rates, you know, I said you're doing a sweep over the S param or sweep over frequency. You don't have to do like circle fitting, right? You just have a loss rate. I just know the extent to which this qubit coupled to the continuum. There's no like circle fitting to find a loss rate. But really, I think the attractive feature of this is the ability to do n-dimensional sweeps super easily without needing to sweep in HFSS, you know, over n dimensions. So one kind of nice use case. So this method is really, it's for finding problems. So this is some, you know, not good data from one of our systems. So this is looking at the T1 of a tunable coupler that we had. And, you know, we noticed, you know, there's sort of like some tricks you can do to measure the T1 of your tunable coupler. And we found that, so we did a simulation, had an actual tunable coupler, and then we were measuring its T1. And, you know, we could see that the T1 of it was not very good. It was also very smooth. So this plot here is just showing measuring using a few bunch of different qubits, you know, the qubit on the left, qubit on the right, combining them together, measuring the T1 of the tunable coupler. You know, we saw some pretty clear agreement. So this just sort of gave us confidence we were measuring it correctly. And then we ran this simulation method. We pull out a whole bunch of loss rates to every single port. And we end up finding that the loss rate of the tunable coupler to its flux port is like very, very high, you know, way higher than it ever should be. You know, there was sort of some like return current issue that we'd had. And then when we actually ran the simulation, compared it with this total T1 and plotted it, you know, we found some pretty nice agreement. This was not like a fit. This was just calculated what is my, you know, predicted per cell channel, you know, what is the T1 of this tunable coupler. And you know, we found some pretty nice agreement. And not only did we find agreement, it told us exactly what was going wrong. It told us exactly which loss channel. Again, you could do something like, you know, EPR to find the same thing, but this one also works really nicely to sweep parameters. Like I can sweep really nicely, you know, and find out what the tunable coupler loss rate is, and, you know, sort of the frequency dependence really tells you a lot of extra things. Also, then you can sort of look at what's the qubit loss rate as I sweep the tunable coupler frequency. Maybe as I sweep the qubit frequency, right? If I have a really strong per cell channel on my coupler, I've probably got a per cell channel on that qubit too. So the ability to sort of actually explore this parameter space worked really nicely for us. So this was just kind of like one case where this technique ended up kind of telling us where we'd gone wrong and helped us fix an issue. And that's all.